All right, so this video we want to do is we want to look at the energetics of solution formation. So we take two different things, we mix them together. What's going to happen when we mix them together? Are we going to get those two substances to release heat? Is it going to be exothermic when we mix them together? Is it going to feel hot? Or is it going to absorb heat? Is it going to be endothermic when we mix them together? And for us to understand this conceptually, what we're going to do is we're going to break it down into 3 steps. Those 3 steps are going to be kind of just blasting apart all of our solute particles to saying we're breaking all the attractions present within them. After that, what we're going to do is we're going to think about then we're going to need to make a little bit of space in our solvent for those solute particles to kind of fit into our solvent. And then finally, we're going to think of, well, when those solute particles actually fit into our solvent, what kind of attractions do they have present that were there now that weren't there before? And so let's go ahead and look at those 3 steps here. So our first step is thinking about completely separating all of our solute particles. Why would you say they're completely separating? Remember, we said our solute in our previous video, we said our solute is the minor component, so it's going to be the thing that's going to break apart the most and separate the most. And so because of that, we're going to think of it as being kind of together as all of these particles like stuck to each other, and then now we're going to separate all those things away from each other. And so here what we're doing is we are going to break whatever kinds of attractions are holding those things together. And we think back to when we talked about reactions and enthalpies and heats. Anytime we broke bonds, it takes energy, right? We have to pull those 2 atoms apart from each other. And so because of that, it's going to be endothermic. We have to put energy in to break those things apart. Same idea here. If we're going to break attractions, that is going to be an endothermic process or with positive enthalpy change. We have to add energy in to make those things separate from each other. And so we think of what kinds of attractions could we be breaking for a solid solute, a liquid solute, or a gaseous solute. We're going to see we're going to differentiate between those. So a solid solute, here we can have maybe like an ionic compound. When we have an ionic compound, we would think, well, what's holding those ions together? And what's holding those ions together are ionic bonds. So we have an ionic compound, we actually have to break apart those ionic bonds that are holding them together. So if we have something like potassium iodide, we have a potassium ion and an iodide ion, we have to separate them, break apart that electrostatic attraction, which would be our ionic bond. Whereas if we have something like a molecular compound that is our solute, maybe something like glucose or fructose, some kind of sugar molecule. That sugar molecule is not an ionic compound. It's not built of a bunch of different ions. It's made of discrete molecules. And so those discrete molecules could interact with each other, maybe if they're nonpolar, by London dispersion force attractions. So we could have London dispersion force attractions, maybe they're polar molecules. And those polar molecules are attracted to each other by dipole-dipole attractions. And then if it's maybe something that contains the ability to undergo hydrogen bonding, where we have a hydrogen directly bonded to an oxygen, nitrogen, or fluorine in that molecule, then we would see that we would have the ability to also have hydrogen bonding. So we have all 3 of those possible interactions that we may have to break for our solid solute, right? Some examples of that would be like our potassium iodide for our ionic compound. Maybe we have something like naphthalene for our molecular compound. That's a molecular substance that contains a bunch of carbons and hydrogens, and it's a large molecule that would be a solid at room temperature. Where we have our dipole-dipole attractions. Maybe this is something like our carbon tetrafluoride, where we have these molecules where we have a polar molecule, where we have maybe a fluorine on one side of our molecule and some hydrogens on the other side, and makes it polar. And so then we have these dipole-dipole attractions, or we have hydrogen bonding. Maybe we have our glucose molecules, where we have oxygens bonded to hydrogens, and so then we have the ability to undergo hydrogen bonding. Then we go to our liquid solute. Maybe we're going to dissolve a liquid in another liquid. And again, we're not going to really think of our ionic compounds being liquid solutes, because these ionic compounds for them to be liquid is going to be at a very, very, very high temperature. And if that's the case, we're not really going to be making these solutions that contain a liquid as our solvent. So we're really only going to have molecular compounds, and that would mean we have the ability to undergo break apart London dispersion force attractions, dipole-dipole attractions, and hydrogen bonding attractions that we'd have between those different molecules. So why don't you go ahead and pause the video and answer the question, what types of attractions do we have to break to separate gaseous solute particles? Maybe I'm going to take something like carbon dioxide gas, and I'm going to dissolve that into water. So that would be our solute, it would be carbon dioxide. What kinds of attractions would we have to break between those carbon dioxide molecules to allow it to dissolve into water? So now as you got a chance to predict what you think the types of attractions that we have to break between gaseous solute particles, what you'll notice is I said there's actually no attractions that we need to break. Now, why would we say that? Even though we may have a polar substance or something that has oxygen bonded to hydrogen to give it, that can do hydrogen bonding, or maybe a nonpolar substance, those molecules are so far apart from each other that they don't see each other. So effectively, we're already at this place. We're already at the place of those molecules being separate from each other, that we don't actually have to add any energy in to separate them again. They're already separate. There's no attractions present between those separate gas molecules. And so we actually don't have to add an energy in to break apart those solute particles. That's already been done by the fact that they are in the gas phase. So that's kind of first step. And again, we're conceptually breaking this apart. This is not actually what happens. We don't blast apart a bunch of sodium and chloride ions, and then they're separate, and then all of a sudden they dissolve in water. We're thinking of kind of our separate processes that need to happen for something to dissolve in another substance. So then secondarily, we're going to think about, we have our solvent. Now we have to make space for our solute to dissolve in our solvent. So if we now have these kind of individual either molecules or atoms that we have for our solute, those kind of individual molecules or atoms are going to need to fit into empty spaces in our liquid. Okay, and again, we are going to be kind of breaking some attractions. And here, these again would be intermolecular force attractions. Now, when we break attractions up here, with our solute, we're breaking all of those attractions. We're completely separating them. Whereas when we're thinking about our solvent, we're just kind of spacing them out a little bit to give room for our solute to dissolve in there. So again, this would be endothermic. Now, even though this is endothermic, this is going to be much smaller in magnitude than we would see for our solute particles, because we're only kind of making space for it. We're not totally separating them. And now if we have a liquid solvent here, we're going to focus on our liquids being a solvent instead of a solid or gas being our solvent here. So we have a liquid solvent. Again, we have the ability to have a molecular compound. And again, that molecular compound could be polar or nonpolar or have the ability to undergo hydrogen bonding. So we may have to break some London dispersion force attractions, some hydrogen bonding, intermolecular force attractions, or some dipole-dipole attractions. So again, this depends, when we say this, it depends on what our solvent is. Likewise, when we measure this for our solute, it depends on what our solute is. Is it nonpolar or is it polar? Maybe does it have nitrogen bonded to hydrogen that can undergo hydrogen bonding? Okay, so now we are at this place where we've blasted all of our solute particles apart. We've made room inside of the solvent for those solute particles to go in. And now those solute particles are going to get mixed into the solvent. So now we've made space. And so now all of these solute particles are going to kind of move in and occupy the empty spaces that have been made within our solvent. So now when we mix these things together, we are now forming some kinds of new attractions. Okay, and so we think of when this is happening, what kinds of new attractions are we making, and does that affect whether it's positive or negative? So again, we broke attractions in step 1 and 2. Now we're making attractions, like when bonds are formed, it releases energy, it releases heat. When we form these new attractions, this is also going to release heat. And so this would be kind of our exothermic step, where we have a negative enthalpy change. So we think, what kinds of attractions can we have if we have a solid dissolving a liquid, or a liquid dissolving a liquid, or gas dissolving in a liquid? So once you go ahead and pause the video and think about what kinds of new attractions would be present if we were to dissolve a solid, and what kind of solid we would have into a liquid, and what kinds of new attractions would be present there. So why don't you go ahead and fill that in on your table. So now as we had a chance to do this, let's go ahead and see what kinds of attractions would we form now that weren't present before. So again, if we think of an ionic solute, an ionic solid solute dissolving into something like water, we now, as we discussed in a previous video, we have these ion dipole attractions, the presence of positive, maybe potassium ion interacting with the negative side of our polar water molecule. Now, if we have a molecular solute, something like a sugar molecule dissolving in water, now we're going to have new types of attractions that are present for these molecules, whether it be London dispersion force attractions or dipole-dipole attractions or hydrogen bonding. And again, that depends on the type of solute, and also depends on the solvent that we are mixing together. Now we have a liquid dissolving into another liquid. Again, we're thinking of, we have these, if we go back up to kind of our liquid solutes, we have these molecular compounds dissolving into another molecular compound. So that would mean we're going to form either new London dispersion force attractions, new dipole-dipole attractions, or new hydrogen bond attractions. Again, that depends on the type of solvent and solute we have. And then as we're taking a gas and dissolving into a liquid, we would see that again, depending on what the gas substance is and what the liquid is, we're going to have those three types of intermolecular force attractions present that weren't there before. Again, that would be our London dispersion force, dipole-dipole, or hydrogen bonding. And so now we think all of these things are happening simultaneously as we take sodium chloride and dissolve it into water, okay? But what we've done is we've conceptually broke it up in our minds to understand what processes have to happen, what kinds of attractions have to be broken, and what kind of attractions have to be formed to allow us to dissolve one substance into another. So we think of the overall kind of process that would happen if we maybe label this as enthalpy change 1, enthalpy change 2, enthalpy change 3, okay? Or we can call this the enthalpy of our solute, the enthalpy change of our solvent, and then that would be the enthalpy change of our solute to solvent, these new attractions that are present there. We would say the overall process that's happening is what we call the enthalpy of solution. So that would be the change in enthalpy for the formation of a solution, and whatever that solution is, right? It could be sugar dissolving into water, or isopropanol dissolving into water, right? There's all these different mixtures that we can form, or solutions that would be formed. So we can think of it as being the sum of all of those different steps, kind of applying this idea of Hess's law. So we'd have the enthalpy of our solute, the enthalpy change of our solvent, and the enthalpy change of our solute to solvent attractions. And again, how positive or how negative those values would be, again reminding us that these would be positive here, and this would be negative, depends on the types of attractions we're breaking and the types of attractions we're forming. And so now what I would ask to do is I would like for us to take this idea of a solute dissolving into a solvent, and why don't you go ahead and predict the sign of the enthalpy change when ammonia gas is dissolved in water. And I want you to say the overall enthalpy change. Is it going to be positive? Is it going to be negative? Is it going to be close to zero? What do we think here? The enthalpy of solution is going to be positive? Is it going to be negative? Or maybe we're going to say it's going to be close to zero. There's really no change that's occurring here. And so what I want us to do is I want us to be able to identify. So I want you to go ahead and predict and identify whether you think it's going to be a positive, negative, or close to zero enthalpy change for the enthalpy of solution. And then go ahead and maybe give a reason for that, like why you would predict whether it be positive, negative, or zero based upon the specific solute and solvent when we're making this solution. So now as we look at this, hopefully we were able to predict what we would think the sign of our enthalpy change would be when we take ammonia gas and dissolve it into our NH3, or sorry, into water to make this aqueous ammonia, NH3. And so for us to look at this, we want to think, what is the molecule that we have? What's the physical state that it's in? How does that relate to what's happening when it dissolves in water? So here we have ammonia, NH3. We notice that this is a polar molecule. And not only is it a polar molecule, it has nitrogen directly bonded to hydrogen, meaning it has the ability to undergo hydrogen bonding. And so we think of maybe the distinct steps that we would have, right? We would have, when we think of the enthalpy of solution, that would be the enthalpy of solution is the enthalpy of our solute breaking apart, the enthalpy of our solvent making some space for that, and then the enthalpy of those new solute-solvent interactions that we'd have. So we think of the enthalpy of solution of our solvent, we notice that this is in the gaseous physical state. So effectively, that would be zero because we don't have to break apart those ammonia molecules. They're already separate as they are now in the gaseous states. We don't have to add any energy in to break those attractions. There are no attractions. They're so far apart from each other. Then we have the enthalpy change of our solvent. Again, that would be positive. We got to make some space for these ammonia molecules. And again, we're not breaking all of the water attractions. We're only moving them apart to make some space for those ammonia molecules. And then we're going to have our solute-solvent interactions that weren't present there before. And again, that will be negative. Now, will this be more or less negative than our solvent interactions? Well, here we have an ammonia molecule, and that ammonia molecule is now going to interact with a water molecule. And we think, well, what kinds of interactions can those two molecules have? We're now going to form these new strong hydrogen bonds. Well, those new strong hydrogen bonds are going to create a lot of really strong interactions. And that is going to make this more negative than that positive value that we'd see for the enthalpy of our solvent because we only separated slightly those water molecules. And so because of that, that would make our overall enthalpy of solution negative. And we would notice that this would be the case for most gas molecules because those gas molecules, we don't have to break those molecules apart. They're already in the gaseous phase. We're just going to add them, form these new attractions that weren't present there before, and we're going to have the release of energy, especially if we have something like ammonia that's forming these really strong hydrogen bonds between ammonia molecules and water molecules. And because of that, we're going to release heat as that happens. So now hopefully as we kind of look through these energetics, we were able to identify what kinds of attractions we're breaking, what kind of attractions we're forming, and how that relates to the release or absorbance of heat when we mix them together. And so we can go ahead and create kind of a generalization of what is going to happen when we mix two different substances. And again, if we have weaker interactions and we end up with stronger interactions as we go from separate solute and solvent to solute and solvent mixed together, that's going to be a process where we are making stronger interactions. And so then that would be exothermic. It's going to release heat when that happens. Whereas if we have the opposite, where we have stronger interactions, and then we mix those two substances together, and we end up with the net weaker attractions that we'd have between those solute-solvent molecules, and that's going to lead to heat being absorbed or an endothermic process. And so now we're able to look at kinds of solutions that we can make, what our solute and solvent would be, and how that would relate to the energetics of them. And has everything to do with how much energy is needed to break apart our solute, how that relates to the attractions then made between our solute and our solvent, and whether they're stronger or weaker, and that's going to lead to a release of heat or absorbance heat when that solution is formed.